In this lesson, we will discuss the RSA algorithm. Before we begin talking about the RSA algorithm, let's think about the following hypothetical situation. Suppose Alice wants to send a secure message to Bob, but they have not had previous contact, and they don't want to wait to send a key for a crypto system. So Alice wants to send Bob a message, but they can't send a key for a classical crypto system because if the key is intercepted, then any transmission that they send will be compromised. And they're going to assume that whatever they send might be intercepted by someone. We'll call them Eve. So the solution to this type of problem is what we call a public key crypto system. So in a public key crypto system, the encryption key is public, but the decryption key is private. So in this system, Bob could publish his public key, and so that anyone could encrypt a message and send it to him, and then Bob would keep the decryption key private, and so he's the only one who can decrypt the messages. So the concept of a public key crypto system was first made known to the public by a paper written by two researchers, Diffie and Hellman, in 1976. And in 1977, three researchers at MIT, Rivest, Shamir, and Adelman, developed the most successful implementation of public key cryptography, known as the RSA algorithm, named after the three authors. In 1977, they developed the RSA algorithm, which was the most successful implementation of public key cryptography, and it was based on the fact that it's hard to factor very large integers. So it's public key, and it's based on fact that it's hard to factor very large integers. In 1997, a British agency, CESG, released documents that showed that two of their researchers actually created the concept of public key cryptography and an actual form of public key cryptography before Diffie and Hellman and the RSA algorithm, but these documents were classified. So in 1997, a British agency called CESG declassified documents showing that in 1970 James Ellis actually discovered public key cryptography. And in 1973, Clifford Clocks actually developed a form of RSA. So there's a little bit of the history of the RSA algorithm. Now let's see how the RSA algorithm works. Again, assume that Alice is trying to send Bob a secure message. Okay, so Bob chooses two distinct large primes called P and Q. And then he multiplies them together to obtain the modulus we'll call it N, which is P times Q. And we're going to have congruences mod N. Recall that phi of N, the Euler phi function of N, would be phi of P times phi of Q, so that would equal, and since P and Q are both prime, this will equal P minus 1 times Q minus 1. Okay, so Bob chooses these two large primes, and we're talking like primes with more than 100 digits. So two large primes. And then Bob chooses an encryption exponent, which we're going to call E. And he chooses it in such a way that it's relatively prime to phi of N. So since the GCD of E and phi of N is 1, since they're relatively prime, we can find the inverse of E mod phi of N. So E has an inverse mod phi of N. So we're going to call this inverse D, and this is going to be the decryption exponent. Okay, so D is the multiplicative inverse of E mod phi of n. In other words, D times E will be congruent to 1 mod phi of n. And Bob chose the primes P and Q, and so he can compute phi of n, which is P minus 1 times Q minus 1, and he chose E, so he can solve for the decryption exponent D. So Bob can find the decryption exponent D because he knows P, and Q. And he can compute phi of n. Okay, so now Bob's set up for receiving encrypted messages. Bob actually sends the public key, which will be the modulus n and the encryption exponent E, to Alice. So Bob sends n and E, so this is the public key, to Alice. And again, this may be intercepted by Eve, but it's okay. So anybody can know the public key. But Bob keeps the integers P and Q and the decryption exponent D secret. Okay, so now Alice will encrypt her message. So Alice writes her message as a number M, and breaks it up into blocks that are smaller than n. So for now, let's just assume that M is less than N. Okay. So Alice has her message M that she's going to encrypt. The way she does it is she computes M to the power E and reduces it mod N. The ciphertext, we're going to call that C, which is going to be congruent to the original message M raised to the power E and reduce mod N. And then she sends the ciphertext C to Bob. Okay. Well, then Bob uses the decryption exponent D to compute C to the power D, which will be congruent to M mod N, and therefore he can read the original message. So let's summarize this process. So first, Bob chooses secret prime numbers P and Q and computes the modulus N, which is P times Q. Then Bob chooses the encryption exponent E such that E is relatively prime to phi of N. Then Bob computes D, the decryption exponent, which is the multiplicative inverse of E mod phi of N. Bob makes N and E public so anybody can send him an encrypted message, and keeps P, Q, and the decryption exponent D secret. Alice takes her message M and encrypts it by raising it to the power E and reducing mod N. She takes this encrypted ciphertext C and sends it to Bob. And finally, Bob decrypts the message by computing C to the power D and reducing mod N to retrieve the original message M. So now let's discuss why the RSA algorithm works. Well, it's based on Euler's theorem. Recall that Euler's theorem states that if A and N are relatively prime, so if the GCD of A and N is 1, then A raised to the power phi of N is congruent to 1 mod N. So in our situation, we have a modulus N, which is P times Q, and we have phi of N, which equals P minus 1 times Q minus 1. And we required that D times E is congruent to 1 mod phi of N. So since D times E is congruent to 1 mod phi of N, we can write D times E as an integer multiple of phi plus 1. So we can write D times E as 1 more than a multiple of phi of N. So 1 plus K times phi of N for some integer K. Then C to the power D is congruent to M to the power E raised to the power D. This is M to the power D times E. And I previously wrote that as 1 plus K times phi of N, so this is congruent to M to the power 1 plus K times phi of N. And I can rearrange this. I can write this as m to the first power times m to the power phi of n raised to the power k, which is just congruent to m times 1 to the power k. So this is just congruent to m when I reduce mod n. So now let's see an example of the RSA algorithm. So Bob chooses his prime numbers. P will be the prime number 885320963, and Q will be the prime number 238855417. Okay? Then the modulus for these calculations will be n, which equals p times q. It's going to be 2114630770206571571. And then he also chooses an encryption exponent. Let's let the encryption exponent be 9007. Okay, so 9007 is relatively prime to phi of n. Now, the public key will be n and the encryption exponent e. So Bob sends n and e to Alice. And again, if Alice wanted to encrypt a message that is longer than the modulus n, then Alice would need to break it up into smaller pieces and then send those one at a time. But let's just start with a really small message here. So let's pretend Alice's message is cat. So she needs to encode this first as a number, and with classic crypto systems, we often let A be represented by the number 0 because you're working mod 26. So A would be 0 and then all the way up to Z, which would be 25. But we don't want to do that. We actually want to start numbering the letters with A as number 1. So we're going to start numbering the letters . So A is going to be 01, B is going to be 02, C is going to be 03, all the way up to Z, which will be 26. Okay, so we don't want to start with A as 00 because if a message began with A, which is 00, when Bob goes to decrypt the message, it'll begin with 00 as well, and so he wouldn't see the A would just disappear and when he decrypts the message. So we're going to start with our numbering like this: A is 1, B is 2, C is 3, all the way up to Z, which is 26. So in this system, then the message is M, which is going to equal 30120. So that's how she would encode the word cat. Then Alice would compute the ciphertext. So it's the ciphertext C, which is M raised to the power E. So this is 30120 raised to the power 9007. Which, when you reduce, mod n will equal 11355859035732866. So there's the ciphertext that Alice would send to Bob. So she sends C to Bob. Then Bob, since Bob knows P and Q, he can figure out the decryption exponent D. So he computes the decryption exponent D. Such that D times E is congruent to 1 mod phi of n. So we could use the Euclidean algorithm, for example, to solve this. This can be computerized so you can find the decryption exponent, but it requires knowing P and Q. So he can compute D, and in this example, the decryption exponent D is 11640247153538991. So Bob takes the encrypted message C and computes C to the power D, and then it reduces mod n, and out pops the original message 30120. So now let's discuss why the RSA algorithm is secure. So the security rests in the fact that it takes a very, very, very long time to factor a large modulus n. So recall, Eve could be intercepting any transmissions from Alice to Bob. So even if Eve intercepts the modulus n, the encryption exponent e, and the ciphertext c, she won't be able to compute d, the decryption exponent. Because she can't factor the large modulus n. So it takes a really long time to factor these large numbers. Therefore, there's no way that Eve will be able to compute the decryption exponent d in order to decrypt the message. As an example of how hard this is, when RSA was first made public, the authors issued a challenge called the RSA challenge. So they encrypted a message and they challenged anybody to decrypt the message. And they gave a small reward if anybody could decrypt the message within 8 years or something. So this is in 1977. So they challenged people to decrypt a message by factoring a modulus n with 129 digits. So this was called RSA 129. Nobody factored the modulus within the given time period of the challenge, but it was actually factored in 1994 by a team of over 600 volunteers. Using a total of over 1,600 computers. So even with improved computing power, the RSA algorithm is still secure because it takes such a long time, even using the best techniques and the best computing power that we have today. It takes such a long time to factor the modulus n. And that's the only way, feasibly, that you can find the decryption exponent d. So let's finish up this lesson by talking about a couple of applications of the RSA algorithm. One of the first applications is sending a key for another crypto system. So it turns out in practice, the RSA algorithm is not quite fast enough for sending massive amounts of data. So there are other crypto systems which are better at sending massive amounts of data, but they're not public key systems. So the key for these faster systems must be kept secure. So the RSA algorithm can be used to send the symmetric key to be used with the faster algorithm that's going to be used to send these massive amounts of data. So RSA has been used to send a key for faster encryption methods such as the data encryption standard, or DES, So the DES, the data encryption standard, was the national standard of crypto system algorithm used in the United States from 1977 to 2002. So this is not a public key system. It's essential that the key be kept private for DES. So you can use the RSA algorithm to send the key, and then the data encryption standard was used to send massive amounts of data more quickly. Another example of an application of the RSA algorithm is a digital signature. So suppose Alice has a document and Bob agrees to sign this document. So this is all done digitally. Then how can Alice be sure that Bob was the one that signed the document? This is the problem of digital signatures. So Alice has a document that is called M that Bob agrees to sign. Okay, so we're going to use the same setup as our example. So as before, Bob chooses primes P and Q, and an encryption exponent E. He computes the modulus N, which is P times Q, and the decryption exponent D, such that D is the multiplicative inverse of E. So D times E is converted to 1 mod phi of N. So Bob takes the message, the document M, and he actually raises it to the power D this time, which is the decryption exponent. So this will be Bob's signature. So Bob's digital signature is, it's called Y, which will be congruent to the document M raised to the decryption exponent D, and reduces it mod N. And he sends Y to Alice, who then raises Y to the power E. So let's call this Z. So she takes Bob's signature Y, raises it to the exponent E, and reduces mod N. And she can do this because E and N are both made public. So then Alice looks at her computation Z, which is Y to the power E. If Z is congruent to the original document M, then Alice can accept the signature as valid, since only someone with the private key D could have signed this document. So if Z equals M, then Alice accepts the signature as valid. Since only someone with the private key D could have signed the document. So these are a couple of applications of the RSA algorithm.